So today we are looking at a very important topic in chemistry, and this will serve as the basis of you doing some further chemical analysis. If you understand this topic well, you will be able to analyze the periodic table, and you will be able to attempt most of the questions that might come up from this particular topic. So today I would like you to go through this teaching very extensively for you to have a mastery of what it's all about. Trends in the periodic table. In 1964, a Russian scientist called Dmitry Mendeleev was a fundamental scientist, one of the best scientists that helps to give the proper analogy, the arrangement of elements in the periodic table. However, John Newland, who was an English scientist, listed all the known elements by their atomic masses. Elements with the least amount of mass were first arranged, then followed by those that have the greater masses. In 1869, Mendeleev helped us to develop a chart which comes with a column and row. The column are called family or group, family of elements. He looked at their chemical and physical properties, and he grouped them based on these parameters. Family contain elements with similar properties. We have both rows and group. The one in the row horizontally, we call it period, while the one vertically, which we call group, actually contain elements that are arranged based on the valence electron in the outermost shell. So left to right across the period, elements increase in atomic number. So when we look at the graphical representation of the periodic table, and as you move from the left to right, you will see increase in the atomic masses of this element from hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. That is the first 20 elements in the periodic table. So Mendeleev believed that there were more elements that will be added, and he left a place for them in the chart so that subsequently, as we synthesize some other element or we discover more elements, there is always a place to put them in the periodic table. Now, looking at the modern periodic table, this serves as the bedrock upon which we need to build our knowledge, because without we having extensive knowledge about how the periodic table looks like, the modern periodic table, we might not be able to look at the trend, because the trend gives us direction as to what happens across the period and then the group. Now, if you have to list the element according to their atomic number, you don't have to be afraid. Go through the modern periodic table. They are arranged hierarchically based on their atomic number. Then we can still use the Mendeleev actually used column, and he called it families, which consist of elements with similar properties. Then coming to the rows, elements increase by 1. As you move from the left to the right, helium actually has 1 electron more than hydrogen, and lithium has 1 more than helium. That is the trend across the period in the periodic table. Now, of course, I have told you in previous classes, if you have not been watching our videos on YouTube, I would advise you that you do. In our previous class, we looked at the 118 known elements, 90 naturally occurring, and why the rest are synthesized in chemistry laboratory for further chemical analysis. So you may need to revise this. So today, let me quickly take you through periodic law before we begin to look at the trend, because this will synthesize and give you an intensive knowledge about what the topic is talking about, and it will help you to navigate your way through this teaching. So periodic law, when elements are arranged in order of increasing atomic number, there is a periodic pattern. Note, periodic pattern in their physical and chemical properties. This serves as the law that we must imbibe or we must follow if at all we are doing anything or playing around the periodic table. The periodic law must hold. If you actually fail to follow the periodic law, you cannot properly appropriate learning or properly understand the concept of the trend in the periodic table. Now, today, quickly, I'm going to run through what you must know at the end of this lesson. Number one, you must identify all the elements in the periods and groups of the modern periodic table. It's very important. You know the atomic number, you know their chemical symbol, you know their atomic masses. This will give you a very good ground for you to build your knowledge. So if you go through this lesson to the end, you are going to be able at the end of this lesson to identify all the elements in the periods and the groups of the modern periodic table. Number two, you're going to understand the properties and locations of metals and non-metals in the periodic table. Number three, you're going to be able to enumerate the pattern, the trend of ionization energy within the periodic table, both across the period and down the group. Four, you're going to itemize the pattern, the trend of electronegativity within the periodic table, both across the period and also down the group. You are also going to be able to highlight the pattern of valence electron within the periodic table across the period and down the group. So you will notice that two things is coming up simultaneously. It's coming up. We're looking at both across the period and down the group. That is what brought about the trend. We are looking at the trend, the pattern. We want to look at the consistency in the arrangement of these elements in the periodic table. So before the end of this lesson, you should be able to discuss the atomic radius within the periodic table across the period and down the group. And you're going to explain the trend of ionic radius. There's a difference between atomic radius and ionic radius. I'm going to explain extensively as we go on in the lesson. So don't mix the two up. If you look at previous questions, WAEC questions, JAM questions, you're going to see that these questions comes most often you see this question coming up from atomic radius and ionic radius. They are never the same. There's a difference between ionic radius and atomic radius. And also, lastly, you're going to be able to understand the metallic properties within the periodic table, both across the period and down the group. And I'm going to show you experiment. We are going to use magnets. In the course of this teaching, we use magnet to experiment all this trend, looking at the ionization energy, looking at electronegativity, looking at metallic properties, look at valence electron, atomic radius and ionic radius. And finally, in the course of this teaching, I'm going to use magnets. We're going to experiment all these trends, starting from ionization energy, electronegativity, atomic radius, ionic radius, valence electron, metallic properties. We are going to use a magnet in order to experiment all these concepts, and I assure you, you're going to get the best. So let's give it a go. Now, let's start with metals. If you understand your periodic table very well, you will understand that metals are in group 1 of the periodic table, and they are located towards to the left of the staircase. They are the first existing elements as it is arranged in the periodic table. And if you look at their state, the state of metal at a standard temperature and pressure, which we call STP, all are solid except a liquid, except mercury. Now, if you look at the general properties of metals, you understand that metals generally are malleable. All these are very important so that you understand how this trend, how it works. You're going to follow the trend and the pattern, because without you having this understanding, you would not be able to understand the trend. So generally, metals are malleable. That is, they can be bent into different shape. You can bring different shape out of them. They are ductile, and they have lustre, they are shiny, they are good conductor of electricity and of heat, and they have high melting point. MP means melting point and BP means melting point. So, and you need to understand that they have low ionization energy, they have low electronegativity, they lose electron to form positive ion with smaller radar. This is very important. I've seen this in time past, in past questions. You need to know that metals generally have low ionization energy. The energy with which electrons are lost from their valence shell, the trend is very low. So they have generally low ionization energy. They have low electronegativity. They lose electron to form a positive ion with small radar. Now, looking at non-metal, we are looking at the comparison between metals and non-metal, because as you move from the left to the right part of the periodic table, you're going to see the metal, the alkaline earth metal, the metalloid. Then you're going to go through the non-metals, the halogens, the noble gases. So it's very important you know the basic concepts and the properties of these elements, which will give you the prerequisite, which will give you the understanding of what you need to know. Now, looking at the non-metals, they are located to the right of the staircase of the periodic table, and generally looking at standard temperature and pressure, all are solid except for hydrogen, for helium, for nitrogen, for oxygen, for fluorine, for chlorine. Apart from this, all others are solid at, remember I said standard temperature and pressure. Generally now, looking at their chemical properties, you know, they are brittle. That is, if they mistakenly fall, they can break, and without amendment, they are dull. They are not as, you know, they are not shining as the metals, and that they have low melting point and low boiling point. Now, looking at the trend, remember our focus in this teaching is to look at the trend. What is the trend of this certain concept? You know, ionization energy, electronegativity, valence electron, atomic radar, ionic radar, metallic properties. These are key concepts of this periodic table that we are trying to demystify and know the trend in the periodic table. So generally, non-metals are poor conductor of electricity. Now, generally, non-metals have high ionization energy. Don't forget, metals has low ionization energy, non-metals has high ionization energy. These are comparison, and this is the basis of our teaching today. You need to compare. Then metals has low electronegativity, while non-metals has high electronegativity. Now, metals tend to lose electron, while non-metals tend to gain electron. For them to be able to attain octet or duplex structure, for them to be able to become a stable element, because if they don't have their orbital completely filled with electron, they tend to be not stable. So let's go ahead. Properties of transition metals. You know, transition metals are between group 2 and group 3 of the periodic table, and I told you in the previous class what these transition metals are. Now, linking the previous class and this class together, you understand that this trend actually has effects on this transition element. Transition metals are generally located in group 3 to 12, and they form colored ion. When mixed with water, they produce colored aqueous solution, and they have multiple oxidation states. For instance, iron has both 2 and 3 oxidation states. Zinc has 2 oxidation states, which is the only transition element without variable oxidation states, because the degenerate orbital is completely filled with electron. So the metalloid are the semi-metal elements, and they are located on the staircase between the metal and the non-metal. They just form the bridge, the gap between the metals and the non-metals, and they are majorly 6 metalloid. And if you look at them, you understand that they are neither solid nor liquid. They are just semi-solid, and this is the basis of their properties. Now, the noble gases, we need to talk about them, because right now I'm going to take you through the trend. But this will give you the background knowledge of what you need to know. Now, noble gases are located at group 8 of the periodic table, and we call them reactive gases or inert gases. Why? It is only these gases that has capacity to have capacity for stability. In chemistry, they are the only gases that have capacity for stability without working or chemically combined with other elements. They are stable, they can stay on their own, they are less reactive. They are not because they are not very reactive because they tend to they are stable already, so they don't allow electron to come into their shell, neither do they give electron. They are just operating on their own. So now, looking at the pattern, let's start with ionization energy within the period. What is ionization energy? It's a good place to start, because without you knowing the concept, the definition, when we begin to use the periodic table and trace the trend, you may actually lose your guard. But amount of energy needed, listen carefully here, the sum total amount of energy needed to remove the most loosely bound electron. I will repeat that. The most loosely bound electron from a neutral gaseous atom. Now, if you are familiar with chemical combination, you will understand that it is only the valence electron that are used for chemical combination. As you look at the atomic structure, inside the nucleus, you have the proton and the neutron. Then you have the electron revolving around the shell. It is this electron, and not just any electron. The electron at the outermost shell, they are the most loose, and that's why I'm saying here the total amount of energy required actually to remove the most loosely bound electron from a neutral gaseous atom. This is what we call ionization. And let's trace it through towards the period and the group. Let's start from the period. Now look at the trend. If you are asked to list the ionization energy for the following element, this is lithium, boron, and fluorine. Look at these three elements. Let's look at them critically, and let's look at the trend from the periodic table. Now you will notice something. You will see that if you are tracing the ionization energy, which is the total amount of energy required to remove the most loosely electron from the atom of a particular element. Now you will understand that as you move from left to right, there's increase from lithium to boron to fluorine. So if you look at the trend, the ionization energy, if that of lithium is 10, boron could be 15, and fluorine could be 20. So it increases only across the period, not down the group, across the period. Now let's look at the group. If you look at it towards the group, now look at the trend. We talk about lithium, boron, fluorine. That is across the period. Now look at beryllium, scrotonium, and barium. Toward down the group, you understand that the ionization energy, instead of increasing, it decreases. And why? Because the ionization energy required for electron to be removed from boron actually is higher than that of barium, and the reason is because the ionization energy decreases down the group. So in summary, or summarily, we say that ionization energy increases across the period and decreases down the group. Now let's talk about the second concept on the periodic table. The second trend we are tracing atomic radius. Now I told you the atomic radius and ionic radius are two different concepts that you must understand towards in the course of this teaching. Now, atomic radius is the distance between the nuclei of identical atom banded together. Remember, the nuclei, the subunit of nucleus of the identical atom banded together, chemically united together, chemically unified together. So the distance between the nuclei is what we call atomic radius. If you look at your mathematics, you will, when you look at the circle, at the center of the circle, the line from the center of the circle towards any other part of the circle forms the radius. So here also, the same thing is applicable in chemistry. When you look at the center of an atom, we call it nucleus. Now, in nucleus, we have different nuclei at different angles that actually performs or are used during chemical combination. The distance between the nuclei is what we call atomic radius. Let's trace it across the period. In period, if you look at it, you understand that atomic radius actually decreases across the period. Remember, ionization energy increases across the period, but atomic radius decreases across the period. So the value actually goes down from left to the right across the period. So if you look at it from the first element, look at the first element, we have a lithium, boron, and fluorine. So if you are asked, can you trace the trend of atomic radius between lithium, boron, and fluorine? You will understand that lithium has the highest atomic radius. And why? It's because the radius in lithium is more higher than that of boron and that of fluorine. So let's look at the group. If you look at the group, you'll notice that the atomic radius, when looking down the group from top to bottom, increases. Ionization energy increases across the period, decreases down the group. Now, atomic radius is the opposite, because atomic radius decreases across the period and increases down the group from beryllium to strontium and to barium. You see the increase from top to bottom. Now let's look at the third concept, electronegativity. Remember, we are tracing the trend, the pattern, because in most WAEC questions you will see these questions coming up often. If you trace it, even almost every 2 years, you see these questions coming up, and it's very important that you have the idea of what this particular concept is all about. So electronegativity, you need to know what electronegativity actually is all about. Just like we examine ionization energy, and I told you that it is total amount of energy required to remove the most loosely electron from the valence set. So electronegativity value of an atom is the measure of its attraction for electron. Please pay attention right here. If you look at the metals generally, that was why I have to take you through the concept of metals, their identification, their position, their physical properties, their chemical properties in the periodic table, because this is what we are using to what we are applying. This is exactly what we are applying right here, right now. So the electronegativity value of an atom is the measure of its attraction for electron. You will understand that metals tend to lose electron for them to become stable, while non-metal tend to gain electron. Because look at fluorine, look at chlorine. Atomic number of chlorine is 17. Remember. Now, in the first cell, you see 2 electrons for duplex structure. Then the next one is 8 electrons for the octet structure. Then remaining 7. It means chlorine is not stable. It's not stable. So for chlorine to be stable, it must actually gain additional electron from a neighboring metallic element. That is what is going to make it to be stable. So let's go and trace the trend from the period and to the group. So electronegativity is the ability of a non-metal to gain electron, usually from a metallic element like sodium, like potassium, like calcium, like lithium. These are metallic elements that actually fraternize. They work with chemically combine with non-metal in order for them to transfer. Sometimes they can share. When we get to chemical combination, you have a better idea. When you talk about covalent bonding, it has to do with sharing. You have to covalently bond together. They will share their outermost electron, but when it comes to ionic, sharing, there is a complete transfer. So electronegativity actually is an identity chemically that actually is attached to the non-metals. Now, looking at the trend, let's go through the period. You understand, if you trace, we are looking 3 elements as a case study right from the beginning of this tracing of the pattern. We are looking at 3 elements: lithium, boron, and fluorine. They are very, very good species, elemental species for us to work with in order to understand the concept of this particular topic. So looking at the trend, you understand that electronegativity increases as we go across the period. Why? The electronegativity of lithium is lower compared to that of boron and compared to that of fluorine. So here, if we ask lithium, boron, fluorine, which one has the least electronegativity? Actually, it is the lithium, because it's a metal. 1, 2, it tends to lose electron. 3, it has the lowest capacity in order to receive electron. Rather, it releases electron instead of receiving electron. So electronegativity actually increases from left to right across the periodic table. Tracing the group now, remember we are looking at both period and group. Let's take a look at it from the group. Now look at this species of element we have been considering and looking at electronegativity. You will understand that beryllium actually has the highest electronegativity, because electronegativity actually decreases as we walk down the group, while it increases as we go across the period. Now looking at the valence electron are electrons in the outer energy level of an atom. Actually, if you look at the energy level of an atom, you have K, LMNO, and across. Then if you look at the trend, you understand that K has the lowest energy, the highest energy level. So but electrons are arranged on the shell. So the valence electron are those electrons are the outermost. Now looking at the period and the group, I have tried to added more elements into the considering elements so that we can have a more broad knowledge about this concept of the valence electron. Now lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. These are species of elements we want to take into consideration, and we are tracing the valence electron both down the group and across the period. You will understand as you go from left to right across the period, you will understand that the valence electron increases. In other words, if the valence electron, for instance, of lithium is 1, that of beryllium will be 2, boron will be 3, carbon will be 4, nitrogen will be 5, oxygen will be 6, fluorine will be 7, while neon will be 8. Look at the trend, look at the increase. So it means as we move from one element to another, only across the period, please note, only across the period, you will understand and you will discover an increase in the valence electron. Let's trace it down the group. Now looking at the group, look at the species of element we have here: the beryllium, magnesium, calcium, and the barium and rubidium, and all. If you look at it now, you will understand something. Now here you need to pay attention. You need to pay a rapt attention here, because I want to explain something very important. If you look at ionization energy, 1 increases, 1 decreases. Electronegativity, 1 increases, 1 decreases. Atomic radar, 1 increases, 1 decreases. Now come to the valence electron. Now we want to look at it on the group, tracing it from the group perspective. In the period, you understand that there's increase, but in the group it remains absolutely the same, because elements are arranged. Apart from the atomic number, they are also arranged in the periodic table based on their valence electron. In other words, as we look at this species of element, look at beryllium, look at magnesium, look at calcium, and other element here, there is a consistency in the valence electron, because beryllium, as it is, atomic number for beryllium is 4, so it has 2 valence electrons. Magnesium has the same though they are in the same group. So beryllium, magnesium, calcium, and the rest of the element, they have the same valence electron. So the valence electron down the group actually remain the same. Let me take you through a principle. There's a principle we apply when we are dealing with the traces, where we are trying to trace the pattern and the trend in the periodic table. We call it PEL. We call it principal energy level. Now, the orbital in an atom form a series of energy level in which the electron may be found. Now, look at it. Each electron in an atom has its own distinct amount of energy, which must correspond to the energy level that it occupies. Now, electron can either be gained or it can be lost, or we can lose an atom or element can lose electron or gain electron, and there must be a movement from one energy level to another energy level. You need to understand this. Now, looking at this, using periodic table as a reference, if you have to look at the principal energy level for period 2 in the periodic table. Now, look at this. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. You understand, if I ask you, what is happening to the number of principal energy level going from left to right across the period? You see that absolutely nothing is happening, because in as much as they are in the same period, the principal energy level remains the same. However, if you trace it down the group, there will be a kind of distort. Either you see increase or decrease. But if you trace it across the period, you understand that the trend remains the same. In other words, this is what we are saying. If you look at your past questions and you see series of elements, species of elements, and they are trying to ask you questions as to what happens to the principal energy level across the period, it remains the same, regardless of the period, whether period 1, 2, 3, 4, or 5, or 1 million, what have you. It must remain the same so long as the elements are arranged on the same horizontal level in the periodic table. Let's trace it down the group. Now, using the periodic table as a case study and as a reference, you will understand that now, instead of the consistency across the period, there is increase down the group. Now, if you look at it from top to bottom in the periodic table, and you want to apply your principal energy level, there must be increase. Why? Because there is an increase in the principal energy level of magnesium, having an added advantage over beryllium. Why? Because beryllium is in which period? Which period? Period 2, while magnesium is in period 3. So that trend gives the analogy of the increase we are talking about as we look at the trend down the group in the periodic table. So if I'm going to ask you now, these elements, beryllium, magnesium, calcium, and the rest of them, which one has the highest principal energy level? So it's going to be what? Harry, actually, because it is actually down the group, and then there's increase from the top to the bottom in the periodic table. I'm not going to close this teaching without telling you about the metallic character. This over time has been surfacing in previous past questions, and you will understand this concept better if you looked at the previous lesson, the concept of periodic table. You check our YouTube channel, you're going to see the lesson on concept of periodic table. So I will urge you to go through that teaching. Now, looking at the metals generally, I have told you metals are re-stratified. We re-stratify metals in order to give their specific and unique characteristics and qualities. Now, most known elements are metals, and most active metals are located in group 1 and 2. So in any group on the periodic table, the metallic properties of that element actually must increase. There is a consistent increase from the top to the bottom. Now, if you look at it, looking at 1 and 2, group 1, group 2 as a case study, now you understand that there is an increase from top to bottom. Now, quickly, before we close, I will look at the ionic radius. Remember, I told you about the atomic radius, and I said the distance between the nuclear within the confine of the nucleus of an atomic, of an atom. So here we are looking at ionic radius. Now atom gain or lose electron to become charged particle called ions. Now you must understand this, please. Metals and non-metals are stratified based on certain qualities, certain characteristics. One of the most profound, very, very sound and very important aspects and qualities and properties of metal is this I'm about to say. Now, metals tend to lose their valence electron in chemical reaction. In fact, for metals to be reactive, 1, for them to be stable, 2, and for them to participate in chemical reaction, most often they have to lose electron. And when they lose electron, they become positively charged. Like, let's take for instance, can we take just some species of element? Now let's take sodium for instance. Sodium, what is the atomic number for sodium? 11. Now 11, if you look at the electronic configuration, which we are going to consider further after this class, I would like you to be consistent and checking our videos on our YouTube channel for updates. Now you understand that sodium has atomic number 11. The first orbital will take 2, maximum of 2 electrons. The second orbital will take 8. That means it will be 1 electron will be left at the valence shell. So that is what is very important and useful for chemical combination. So sodium tends to lose this electron, and when sodium loses this electron, it means it will become positively charged. So sodium and sodium plus is not the same. Please note, Na and Na plus is never the same. Anytime you see any element, whether metal or non-metal or metalloid or transition metal or lanthanide or hafnium, no matter the class, the period and the group, anytime you are seeing any element having a charge, it means such element has undergone a kind of chemical combination, and such element, if it's positively charged, it has lost electron. If it is negatively charged, it has actually gained electron. So metal tend to lose their valence electron in chemical reaction, and this actually enable them to become positively charged. We call them positive ion metals. So the non-metal tend to gain electron in chemical reaction and become negative ion. So at this atom gain or lose electron, they complete their octets valence electron. I love this. I understand and I explained before to you the concept of duplet structure and octet structure, because duplet has 2 maximum number of valence electron, while octet has 8 maximum number of valence electron. So ionic radius, now looking at it, is the distance from the nucleus to the outer principal energy level. Remember, the distance between what? The nucleus, the central atom, the nucleus to the outer principal energy level of the ion. That is ionic radius. Now ionic radius, looking at the trend, when a metal loses its valence electron and become positively charged, then it means that it has lost an energy level. Energy level is lost because electron is lost. So its radius decreases. So when a non-metal gain electron, it means number 1, it has gained more electron has gained more energy level, and then it becomes negatively charged. So the ionic radius of metal is smaller than that of the radius of the original atom. The reason is because there must have been a loss or gain of electrons. So the radii of non-metallic ion are larger than those of original atom. Here, let me quickly take you through within few minutes, using magnet as an analogy. I want to use magnet and demonstrate and show you how the trend works with magnet. Now, looking at the effect of atomic structure on periodic table, remember that all of the elements of the periodic table are made up of the simplest building block, which we call atom. In other words, atom form the blueprints, is the bedrock, is the building block of all matter, because atom actually has subunits, subparticles. So the coming together of these proton, neutron, and electron together, they form an atom. And then the atom now forms the building block for all matter. So the property of element follow general pattern, which we call trend, and that trend is what we have been looking at from the beginning of this lesson. When we observe the property across the period and down the group, this trend can be explained by change in the atomic structure from one element to the next element. So looking at the effects further. Now, remember, first, we look at ionization energy. 2, electronegativity. 3, we look at the atomic radius. 4, ionic radius. 5, metallic property. And now, we want to demystify further using the principal energy level and using magnet as a case study in order to explain this concept better. So, the periodic trend of atomic radius, electronegativity, ionization energy can all be explained using one prerequisite, using one principle. We call it nuclear charge. Nuclear charge. Now, think about magnets and attraction. Have you worked with magnet before? Do you know magnet has both south and north pole? Are you aware that opposite magnet side actually attract while the same pole repel, while different pole, opposite pole actually attract? Now, we are going to base our learning based on this principle. We are going to use this principle as a basis to explain this concept. Now, think about magnet and attraction. Nuclear charge represents the strength of a magnet to attract forces, and the number of principal energy level represent the distance between the magnets. When you put a magnetic property or magnetic substance close to magnet, you will see and understand a kind of pull. The magnet tend to be pulling the magnetic material toward itself. Exactly looking at the principal energy level, we can replicate the same in chemistry. Now, let me bring this to close by looking at the atomic radius first. Look at the group. There's an increase from the bottom or from the top to the down the group. So it means that atomic radius actually increases down the group and decreases across the period, looking at the magnet as a trend. Then atomic radius actually, as we look at the element across the period, the nuclear charge in each successive atom increases. Now, however, the number of this principal energy level remain the same. Please note this, because this is, you are likely going to be seeing this question coming up repeatedly. So therefore, with each successive element, the second shell is pulled closer to the nucleus. So the proximity between the nucleus and the shell actually matters, because there's a tendency of pulling towards the nucleus. So this causes the atomic radius to actually decrease. So we say atomic radius decreases as we look at the group. So conclusion, let me conclude by saying that increased nuclear charge of proton across the period causes the atomic radius to decrease. Please note that. Increase in nuclear charge of proton as we look at the period actually causes or make the atomic radius to decrease. Now, looking at, as we go down the group, the number of principal energy level increases. Therefore, each successive atom down the group actually increases. Very, very important to take note of. So, as the PEL increases, then it means atomic radius also increases down the group. Electronegativity, which is the measure of the relative attraction of an atom for a foreign electron. Now, if you look at it, this diagrammatic illustration, if any foreign electron is coming outside the atom, it has to actually mount the valence electron first, because the attraction is between the nucleus and the nearby valence shell because of the shielding effect. So there's a tendency of shielding the electron at the outermost shell from being pulled towards the nucleus of the cell. So as we go across the period from left to right, of the nuclear charge increases while the PEL remains the same. Therefore, finally, you need to know that from the left to the right of the periodic table, there is an increased attraction for foreign electron, which we call electronegativity. So conclusively, we say increased nuclear charge across the period causes an increase in electronegativity. The same thing applicable to ionization energy. However, the amount of energy required to remove the outermost electron from the atom, which I explained, actually is the same trend. Because of the shielding effect, there's an attraction from the valence electron towards the nucleus. And then looking at it from the right to the left of the periodic table, there is a firm grip of this electron that is closer to the nucleus compared with the one at the valence electron. So the proximity is, if valence electron is closer to the nucleus tends to pull towards itself, which actually the shielding effect will have to actually be overcome before this can actually be actualized. So increase in nuclear charge across the period causes the ionization energy to also increase. So looking at it, let's quickly look at our our exam guide questions, and let's see how we can explore some questions related to this concept that we have just looked at. Now, question 1, which of the following element is diatomic? Looking at it, I gave you the trend with which you are going to actually discover which of these elements as arranged in the periodic table is either monoatomic or diatomic or even polyatomic, because if you go further in quantum chemistry, you are going to encounter some polyatomic element. So looking at the options, we have sodium, oxygen, neon, and iron. Oxygen is the diatomic gas among the options provided. Number 2, the alkaline earth metals have similar chemical properties because I told you this, because they have same number of valence electron, especially down the group. I've explained this extensively. Now, question 3, calcium and magnesium belong to the same group in the periodic table because A, both are metals. No, not because they are just metals. B, they form colorless salt. No. C, they form cation. And D, they have the same number of valence electrons. Are you looking at the trend? Look at ionization energy, electronegativity. So they are taking species, certain element, in order to test your knowledge about this concept. So if you have gone through this teaching, you should be able to understand that they have the same number of valence electron. Now, looking at the next question, which of these following gases is monoatomic? We have oxygen here, argon, chlorine, and nitrogen. So because of the position of oxygen tend to actually form a monoatomic, a diatomic, because it cannot stand on its own. Looking at the octet structure, oxygen is not stable. It's not stable, so it must actually look for an affiliate electron from the neighboring metallic element in order for it to be stable. So here, which one is monoatomic element? We have nitrogen, chlorine, oxygen, argon. Argon, I told you of noble gases. So noble gases are monoatomic, primarily because they have all their orbitals completely filled with electrons. Next question. We have, look at the question here. They gave us a diagrammatic illustration and we are asked to look at it. Which of the letters represent the alkaline earth metal? Oh, I thought this. Alkaline earth metal. If you look at the option, you understand that A, B, C, D, E, F, and G. Looking at how they are positioned. A is what? Hydrogen. B is what? Helium. Then we have lithium and beryllium. It means that C is beryllium. Boron, carbon. That means D is carbon. If you cannot trace this on the periodic table, you cannot answer this question. So the right answer here, we say which of the letters represent the alkaline earth metal? It is C. C, option C is very accurate. Now looking at the next question, which of the following element is diatomic? Actually, diatomic, oxygen is diatomic among the options. Looking at this, which of the element indicates of this element, which of the letter indicate element which exists as a diatomic gases? We have J. J is correct. Option J is correct right there. In the periodic table, now alkaline earth metals can be found in group. That was why we need to look at the trend. Look at it. Alkaline earth metal, they occupy the second group. So option C is actually very accurate. Which of the letters represent an alkaline earth metals? Here, J is very accurate. Now, looking at the trend, we want to look at the last question and look at the trend. Now, use the following portion of the periodic table to answer the question. They gave us an analogy, a pictorial or a kind of graphical representation of this position of the element in the periodic table. Now look at it. Which of the letter indicate element which exists as a diatomic gases? A and E, A and F, C and A, B and J. These are jam questions. These are questions that you cannot but encounter in the course of you exploring most of these past questions. So if you look at the trend, you will understand that looking at diatomic gases, A, which is hydrogen, and F, which is fluorine, both are diatomic, while others are monoatomic elements, so or monoatomic gases. Here we are going to end this teaching for this class. I will urge you to please subscribe to our YouTube channel, and then for you to be updated on our subsequent video and classes on chemistry. Thank you very much for listening. God bless you.